Hey everybody, and welcome back to #Korb Stat Chat. My name is Mr. Korb. Let's talk about some stats. So today, what we're going to talk about is probability theory. So the basic introduction to the whole unit of probability. We're going to go into much more detail here in a little while. In the next couple of videos, we're going to take a probability sort of journey together. So this first section is all about probability. So let's define probability. Probability is a numerical measure between 0 and 1 that describes the likelihood that an event will occur. So how likely something that will occur is all about probability. So we have a 0% chance of probability versus a 100% chance of something happening, or 0 and 1. So how we start to describe this is more on like a continuum. So we have a ton of different types of probability here that we're going to talk about: mutually exclusive versus non-mutually exclusive. We have independent versus dependent probability, but we're going to just start with the basics. So all probability centers around the idea that we have on a continuum between 0 and 1. And you can basically have any probability in between 0 and 1 that you would like. So anything that we have a 0 probability is that we have an impossible event. So we have something that will never occur. Something like when you're rolling a die, a 6-sided die, and probability of rolling a 7. Probability of rolling a 7 is 0 out of 6. So we have no probability of actually rolling a 7, so that's an impossible event. We also have running a certain event. And a certain event is something that will always occur. So the probability of me flipping a coin and getting heads or tails. What's the probability of me getting heads or tails? 100%, because I'm going to get one or the other. So that is the impossible event versus the certain event from 0 to 1 on this probability continuum. And then what we have here in the middle is the famous 50-50, or an even chance of getting something, or equally likely event happening. So the probability of getting heads is 50-50, because you have 50% of the time you're going to get heads, 50% of the time you're going to get tails. Now, we're going to be discussing here in a little bit the difference between experimental probability and theoretical probability. And we're going to base a lot of what we do in stats off of theoretical, with the idea that if we do experimental enough times, we're approaching the probability of the theoretical probability of a certain event. So let's continue on. We're going to start talking about different notations that we're going to use and just run down the basics. And we're going to get into something called the law of large numbers, which is pretty sweet. Okay. So we talk about probability all the time, being the probability of an event happening. So how do we actually note that in statistics is like this. We have P of A, which reads as the probability of the event A occurring. So P of A is the probability of event A occurring. So the probability of event A occurring in a specific situation, or the probability of event A, we're going to use the notation P of A. Okay, got it? So when you see this again, know that that's what we're talking about. So we're going to use proper notation in this section. So probability of event A occurring is the probability of A, so P of A. All right, so moving on, there are actually 3 ways that we assign probability. So 3 ways. So the first way is going to be this idea of intuition. So intuition. Okay, so intuition is the basic probability that we just throw out, like word vomit, right? Because there's no real statistical basis. It's just based off of past experiences. Ones that are really keen on doing this are sports announcers. So they will say that this guy typically makes his shots 90% of the time. Now, that may be founded in some statistics, but they may not be sharing all those statistics with you. So it's just spur of the moment, we assign that probability, but it's our best guess of something occurring based on our prior situations or experiences, right? The second way, which is the most non-reliable method, by the way, so you should know that. So intuition is the first way. Our second way is going to be relative frequency. Which is great because we talked about relative frequency before in a Korb Stat Chat video. One of our first episodes, we talked about frequency tables and actually generating relative frequencies, which are just assigned by the frequency out of the total number of possibilities that we have. Not possibilities, but number of trials that we have. So this is really geared towards something that we're observing, an event happening. So if we're looking at shooting percentages of players and actually have those statistics that we're going to use, this is where we're going to use relative frequencies. When we have an event happening, typically an experiment, we are going to be looking at the relative frequencies of something occurring and then applying those to predict things that would happen in the future. So if you go in with the knowledge that a certain player has an 80% chance of shooting the basketball and making it in, then you know that out of every 10, he's going to make 8, right? Should make 8. And that's relative frequency and going more into the theoretical and experimental probabilities that we are going to talk about next. Okay, so that's the first way is intuition, second way is relative frequency, and then the last way is equally likely outcomes. And these are more game theory. So if we have like a roulette wheel with all the different spaces on a roulette wheel, each one has an equally likely chance of occurring. Likewise with a flip of a coin. Okay, flip of a coin, we have a 50-50 shot, equally likely chance of happening. Or we have a die, okay, which also has an equally likely chance of occurring. So flip of a coin, drawing a card, are all going to be equally likely outcomes. And that's where a lot of our game theory comes from, game probability theory. So we'll be discussing that quite a bit also in this unit. So the 3 ways, we have intuition, we have relative frequency, and we have equally likely outcomes. Let's move on. Okay, the next thing we're going to talk about is this idea of the law of large numbers. Law of large numbers. And the law of large numbers states this: as the sample size increases, the relative frequencies of the outcome gets closer and closer to the theoretical probabilities that would occur. Okay, so I'm going to repeat that again. So as the sample size increases, the relative frequencies of the outcomes gets closer and closer to the theoretical probability of an event occurring. Okay, so to do this, I'm going to illustrate it via an example. We're going to take a coin, or actually do 2 examples. We're going to take a coin first, and we're going to flip this, right? Now, what should happen if I flip it twice? If it's equally likely outcomes, right? We have the heads, whoop, there it is. We have the heads, we have the tail side. What's the probability of heads occurring? Should be 50%, right? What's the probability of tails occurring? Should be 50%. So if we were to flip it 10 times, would you agree with me that we would have equally likely outcome of 5 and 5, right? However, does that happen typically in experiments? So we are comparing 2 things. So I'm going to boil this down to one sort of idea. Experimental approaches, theoretical. The experimental probabilities of an event occurring will approach the theoretical probabilities of an event occurring if our sample size begins to increase. So if I were to flip this 2 times, what should happen theoretically is it's 1 and 1, right? Between heads and tails. Theoretically, what should happen is if I flip this 10 times, it's 5 and 5. However, what you're going to see, hopefully, I mean, I've done this before, but it's never worked out perfectly. And that's good, because the more and more times that we do it, the more and more coins that we flip, the closer and closer to the theoretical probabilities that we are going to get. So let's take a side sort of step and do this experiment real quick. I'm going to speed it up so you can see the whole thing. Okay? Okay, so what we ended up doing was flipping the coin 20 times. And we ended up getting heads being, we flipped it 20 times and we got 12 being heads. And then we got 8 being tails. So the phrase tails never fails, it failed in this case. Okay, so heads versus tails, what it should have been, and this is going to be the theoretical. Okay, the theoretical should have been heads being 50%. Okay, 50%. So 50% would have been 10 out of 20. Okay, and then theoretically, tails should have also been 10 out of 20. However, what we ended up getting was percentages like 60% of the time was heads and 40% of the time were tails. So 60% to 40%. Now, again, if we would have done this 2 times and we would have gotten tails twice in a row, that means tails, the experimental probability of tails would have been 100% and heads would have been 0%. And you know that that's not the case. You're not always going to get tails. Okay, so what happens here is as these start to increase, so say that I were to not just do 1 coin, but we throw in another coin, right? So now we have two coins, not 2 coins, but we're doing multiple events, right? Over and over and over and over and over again. So we flipped the coin 20 times. Let's say we did that 40 times, or 60 times, or 100 times, and so on and so forth. So you just keep going and going and going and going. And you keep flipping coins, right? And okay, so what happens here is as the experimental increases, the number of sample sizes that we use increases, it's going to approach the theoretical. So what's really cool here is as we start increasing this and say that we did this 1,000 times, you would see that these percentages would start getting closer and closer and closer and closer together because they're equally likely chances of happening. So as we start to increase and we did it 100 times, you may see that it's 51 to 49. And as we do it 1,000 times, you may not see a difference at all. It might come out perfectly even. But we're getting closer and closer to the theoretical value. Now the same scenario happens when I roll a die. Now a die should happen 1 out of 6 times, right? If I just choose a number. So the number 1, probability of 1 occurring is going to be 1 out of 6. Now if I roll this and roll it 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 over and over and over again until we did 10,000 rolls, we might get closer and closer to the 16.7% of the time rolling 1. However, that's not going to happen in experimental, and it will never be perfect to theoretical. Now we may get near perfect, we may get to the closest millionth decimal place, but it will never become the theoretical, which is fine because we just assume that in probability and statistics that we're going to take enough samples in order to apply the theoretical probabilities of the event occurring, especially when we know for a fact that this should be an equally likely chance of happening. Okay, so thanks for watching. This has been Mr. Korb with Korb Stat Chat. This is just the beginning of probability, so stay tuned for the next episode. Peace.